yeah, it's the PIC16F684. Oh yeah, it's the PIC16F684. Wowee, it's the PIC16F684. Yabba dabba doo, it's the PIC16F684. In the world of microcontrollers, small and sleek, there's a chip that's standing strong, not mild or meek.
Hello everybody, and good afternoon. Thank you for watching. Today's video is on the PIC16F684, and more specifically, it's a project where I created code that controls not one, but two shift registers. So it takes in 8 bits of data on the 74HC165 shift register. This shift register is parallel in and serial out, and then I have the code taking this data that it accepts, and I send it back out on the 74HC595. And this other shift register is serial in, parallel out. So up until now, I created this video here, and I created this one here, so part 15 and part 9, and both of these videos show a demonstration of the PIC16F684 controlling those shift registers individually. So what I have done since then is I have combined the two pieces of code into one piece of code so that I can, once again I explained it, but I'll say it again, so that I can take in data with the parallel in and serial out shift register, and then I take that data, which I've stored in one of the 16684's register memory locations, one of them, and then I'll take that byte of data and I will send it out on the serial in, parallel out 74HC595 shift register. This is a side note, which I will mention next here, and that is that I experimented with optimizing my code so that it doesn't repeat these same blocks of code for each bit of data that it takes in. I experimented fixing that and just making the code shorter with no success. So I still haven't fixed that. So now I just have this lengthy code. Alright, so I'll be methodical in explaining my code here, particularly with an emphasis of the changes I had to make to combine the two pieces of code. So I'll start at the top. So these two counters here are for the delay routine, and I won't explain those too much. They go with the delay routine down here, which kind of digresses to try and explain that. And then I created an 8-bit file memory location, and this C2 value is the first value dealt with in the code, and with the parallel in serial out 74HC165, it makes use of this C2 memory location that I've designated, and it will take in 8 bits of data and ultimately store it in this file location, which brings me to a change I had to make this code all work, and that's kind of in the middle here, where it goes from controlling the parallel in serial out shift register to the code where it deals with the serial in parallel out shift register. So kind of the bridge between the two happens here. I'm kind of catching this right now as I'm studying this while I'm recording. This was unnecessary. I didn't need to have 2 different counters. I could have just used C2 all the way through this second shift register. I didn't need to create a separate second file memory location with a name. Oh well, I'll leave it. I'll go with it. And anyway, then it goes through the 595 shift register, and it works through that data that the first shift register took in, and it's going to send the second shift register's data out. This subroutine just clocks in the data. Anyway, it didn't take many changes to get this all to work, as I combined both pieces of code. So the next step I'll just show you on my breadboard setup, and you'll notice, as compared to previous videos I made on these shift registers, you'll see that I actually have a hardwired project that I built, and I felt it necessary in the process to actually build this because doing things on little breadboards with jumper wires started to get really complicated. I'd have lots of wires, so to me it just made sense to build something. And I guess I'll just comment. Funny thing is I don't like sitting down and soldering things and building them. To me, it's kind of fun. The thing I like is having the project that I built. I like owning it, but I don't necessarily like building it. Building it is tedious and it takes a lot of work. But ultimately, the reason I built it is because I think to really progress in this hobby, you need to be able to program a piece of hardware. Unless you're building or writing some code that's just some type of calculator where it just crunches numbers, I think ultimately these microcontrollers are supposed to control hardware. So that is why I went to the trouble. That's why I went to the trouble of building a hardwired circuit.
Alright, so here is the hardwired project that I built. This is the PIC16F684 microcontroller, and this is the 74HC165 parallel in serial out. This is the serial out pin, and these 3 lines here are RA0, which is connected to the serial input pin of the 74HC595 serial in parallel out shift register. So let me see, this line here is RA0, which connects to the serial input. This line here is RA2, which connects to the clock input. And this line here is RA1, which is the latch clock pin, which latches everything at the end. Anyway, to visually see what's happening, I have this little LED module I built set up so you can see what all these pins are doing. So this is just for added visualization, some learning. But these lines ultimately go into the 595 shift register. I'm going to get rid of the light because I think it shows the LEDs better. This is just a counter I created to input random numbers. That's a good number. Low, high, low, high, low, high, low, high. That's great. So now I will hit this push button, which activates the whole code. If you look at the top of the code that I wrote, everything is initiated by BTFSS, I believe. Bit test file skip if set. Or was it the other way around? Yes, that's correct. Skip if set. This push button circuit is a debounced push button which controls a transistor. This is overkill. It was totally unnecessary. I shouldn't have built it so complex, but it works. And I left a female port, so if I didn't want to use the push button and I wanted some other device controlling the push button input, I could have another microcontroller possibly controlling it if I use these input pins. So anyway, there is a push button here which is connected up to the BTFSS beginning part of the code, and it starts it activates the parallel in serial out. It takes a little while because of all the delay routines, but here's the output. And hopefully you can see that the data in low, high, low, high, low, high, low, high is exactly the same on this shift register. Low, high, low, high, low, high, low, high. It's exactly the same. So I have taken the data here, put it through a shift register, through the microcontroller, and back out through another shift register and displayed it. And that might seem pointless, but now I've created something where I could do something with this data and then spit it out here. So I could maybe complement everything or swap F or do some other type of operation to the input data and send it out here. So I'm going to continue building the rest of this circuit. I'm going to get this hardwired into this. So hopefully I'll be able to complete that and maybe work on some more experiments. So thanks for watching. This has been an update video, and yeah, thank you for watching. Let's try one more example.
It's the PIC16F684 with its tiny frame, but don't you underestimate its game. Oh, PIC16F684, you're the heart of innovation, tiny yet so mighty, a marvel of creation. With your power and your speed, we can build it all, from robots to gadgets to standing tall. With your 8-bit core and your flash memory, you bring dreams to life just like alchemy. From blinking LEDs to complex motor drives, you keep our projects running, making them alive. Oh, PIC16F684, you're the heart of innovation, tiny yet so mighty, a marvel of creation. With your power and your speed, we can build it all, from robots to gadgets to standing tall. PIC16F684. You're the heart of innovation. Tiny yet so mighty, a marvel of creation. With your power and your speed, we can build it all. From robots to gadgets, you're standing tall. With your 8-bit core and your flash memory, you bring dreams to life just like alchemy. From blinking LEDs to complex motor drives, you keep our projects running, making them alive. Oh, PIC16F684. You're the heart of innovation. Tiny and so mighty, a marvel of creation. With your power and your speed, we can build it all. From robots to gadgets, you're standing tall. Timers and counters, ADCs and more. With every pin and feature, you open up the door to endless possibilities, to coding to create. With you, PI16F684, we can innovate.